Hello and welcome. My name is Mario. Today I want to show you the new power station Fossibot F2400. I just received this unit and wanted to tell you about it, and I did some extensive tests regarding capabilities and also efficiency. So what have we got here? This is a lithium iron phosphate based power station capable of a maximum continuous output of 2400 watts. The nominal capacity of the batteries is 2048 watt hours. We got several outputs for DC 12 volts stabilized at 13.67 volts. We got several USB outputs, so two quick charge ports USB A, 3 20 watt power delivery USB-C ports, one 100 watt power delivery port, a light. We got on this side we got 3 AC outlets. As I'm in Europe, this is the 240 volts 50 Hertz version. No connections on the rear, and on this side we got the inputs, so direct AC input from the grid and a DC input for charging from solar or your car battery, for example. So here's a mini circuit breaker reset button, and in case you're wondering, the unit features on both sides some pretty hard to open flaps where the vents and fans are behind. So when charging and discharging the unit, these need to be opened. On top of the unit there's a compartment for the cables. So the unit comes with AC cable and 2 cables for DC charging, one for the cigarette lighter adapter and one for solar, so it's an MC4 adapter. On back to the front we of course have the power button, and this wheel is something I've not seen before on a power station. Here we can adjust the charging current or charging wattage, so we can adjust from 300 watt minimum charging power to maximum of 1100 watts. So that's for the feature stuff, and I did some pretty extensive tests. Oh, sorry, forgot the most important thing. There's also a light, so it has a continuous mode and blinking mode and an SOS mode. I just skipped, obviously. So again, continuous, SOS and flashing mode. Yeah, so now for the tests. So now let's try to measure the efficiency at the different charging levels. So we have this rotary wheel here where we can set the charging speed. Let's turn it down. We set it now to 900 watts. Let's settle it a bit. And at 900 watt charging, we are drawing around 970, 971 watts from the wall. Next step, 700 watts. And now we are drawing 770 watts from the wall. $500 setting, and we are drawing 520 71 watts from the wall, and the lowest possible speed to set is 300 watts, and at this setting the unit consumes 371 watts. So it seems that it's fairly consistent. We are drawing about 70-71 watts more than what we are charging into the unit. So efficiency wise, the higher the charging speed, the better the efficiency. So let me turn it back up to maximum to confirm. So the unit takes a bit to increase its charging speed. But now we are back at the maximum charging speed at 1100 watts, and we are drawing 1174 watts from the wall. So efficiency wise, charging it faster is better. For the lifetime of the batteries, it should be the other way around, but on the other hand, even at 1170 watts or 1100 watts, we are just charging at about 0.55 C, so not really fast charging. For lithium iron phosphate batteries, this should be fully okay. So while the unit is charging, let me check the DC output capabilities. So we do have here a 12 volt cigarette style lighter socket, a 12 volt 25 amp XT60 connector, as well as two barrel jacks limited to 3 amps. So let's first test the cigarette lighter adapter. So the voltage output is regulated to 13.67 volts. I've set this electronic load to discharge at the maximum rated 10 amps. So when we turn it on, we see that the voltage does drop a bit, but it still stays at 12.88 volts in this case, at the maximum draw of 10 amps. So next we'll test the XT60 output. So it's connected to the same electronic load, same setting of 10 amps. Unfortunately, that's the maximum this electronic load can do, so I can't do a max discharge rate test here. But when we turn it on, we see that the voltage does say quite a bit less, so it goes on down only to 13.46 volts. Even though it doesn't look like, these cables are higher gauge, so this may be the reason. But again, we are now drawing 135 watts, and nothing gets warm. So this connector I very much prefer, because also when you're on the road or somewhere, this is absolutely sturdy and fixed, and this will never come loose on its own. As for the USB outputs, we do have here two Quick Charge 3.0 boards, and when I connect my old mobile, of course I have to turn the output on, but as soon as I plug it in, phone turns on and it's charging, so it works. And for the USB power delivery ports, I'm gonna charge my power bank here, and when I connect it, we see here it's charging, and it doesn't show details, but we see that it's charging, it's quick charging on the 9 or 12 volt rail, so quick charge is also working fine. I'm still waiting on a power delivery device that can charge at higher rates, so I'll add this video as soon as I receive it. Let's try out some DC charging next. So there's two possibilities. We do get the adapter cable for solar charging with MC4 connectors, as well as a second cable with a cigarette lighter plug adapter. I've plugged this in into another power station. Let's see what happens when I connect it. So on the screen we do get the icon for DC input. but the unit is still charging at 1100 watts. And when we check the smart meter or the smart plug, we are still drawing 1171 watts from there, so no dual charging on this unit. Let's see what happens when we turn off the smart plug. So input first goes to 0, and afterwards it starts charging from the 12 volt input, and it seems to limit itself to 100 watts. Although at the moment I can't tell if this is because of the input on the Fossibot or because of the output on my other power station. Let's try this with a different charging device. So now I'm gonna use my lab bench power supply set to 13 volts because I expect some voltage drop, and the current is turned all the way down. So I'll now plug it into the DC input socket. Sorry, the smart plug was turned on again, so let me turn it off. Although interesting to see, we are now at 86% of charge, and the input has already, I didn't limit it, so it's still set to maximum, but it went down to 550 watts input. So let me turn this off. AC input is off. DC input is turning on. We do get some input here, but as I said, it's still limited by current, so let me increase the current here. I'll go up all the way to the maximum the unit can provide, and it seems we are still limited to about 100 watts input, so 103, 104, although the power supply could deliver up to 10 amps. Now it even turned off. Okay, turned back on again. We are only drawing 8.3 amps, so it seems that the input on the device is limited for 13 volts. So what happens when we increase the voltage? So let's go higher to around 18 volts, which would be solar panel voltage for a 12 volt panel. Okay, I exceeded it a bit. I'm now around 19 volts, and now the unit seems to be allowing a higher current, but the two devices seem not to be very happy with each other. The MPPT controller is fluctuating wildly, sorry. Let me crank up the voltage even higher. The maximum on this device is an input voltage of 50 volts. So the highest I can get now is around 25 volts, 26. So they seem to be negotiating, and we currently have an still increasing input of around 280 watts peak. So shortly I even saw above 300. So 300 watts is the maximum of this device. So again, the MPPT controller and the controller inside this lab bench power supply seem to not be very compatible, but still it seems like at 30 volts we can get up to 300 watts of DC input. So next, let's check the AC output. We are still connected to the AC input, so good possibility to check the UPS mode first. So let's turn on the AC output. We do have a nice voltage here, 220 volts AC, 50 Hertz. So as you see, that's the European model, of course. So we are currently drawing 1411 watts on the output. The input is 1810. That's why the unit is still charging. And when I turn off the AC input, let's see what happens to the voltage. More or less nothing, 1 volt less. So let's do the same again, but this time in oscilloscope mode. So we do have a nice sine waveform that's coming from the inverter, so it's really one of the nicest waveforms I've seen on any power station. And when I turn back on the external input, sorry, that was my fault. The probes do not sit very well. We still have the same nice waveform. Turn it off again. No change. Turn it on again. So the UPS relay seems to work really nice. So, but for the next test, I'll turn off the external input. I now have the unit running at 1350 watts about. And now let me turn on a second load. Sorry for the noise. We are drawing nearly exactly the nominal output of the inverter now at 2360 watts, and the waveform is still very nice. Let's check the voltage. 226 volts. So the output of the inverter seems really nice. So now let's have this unit running for a few minutes at maximum load to see if anything will happen or if it can sustain this output. So the unit has been running at peak load for about 5 minutes now. I've just realized a few seconds ago that the fan seems to have at least 2 speeds, because I realized it switched to a higher speed. But apart from this, we still have a very nice voltage, 225 volts. Let's check sine wave again, very fine. So it seems to have no problems running at maximum speed. But to kick it up a notch, let's try adding another load and exceed the nominal rating. I've now added another load, but it seems that the unit is limiting itself to around about 2400 watts. I heard the heat gun throttle down a bit. Theoretically, I just added another 400 watts, but the output seems to be limiting itself to its maximum capacity. I'm now going to start an AC discharge test. So the unit is fully charged. I have connected an electric underfloor heating pulling roughly 400 watts. So I'll discharge it at a 0.2 C rate, which is the industry standard, and we'll see how much energy we can get out of the unit by using a smart plug connected here. So I'll unplug the charging cable and turn on the smart plug. So currently the system is drawing 353 watts. So this test should take about 5 hours, 4 to 5 hours probably. So the AC discharge test just finished. Let me plug in the power. So the unit turns back on, and as soon as I can turn on the AC output, we should be able to connect to the smart meter. So it seems like we were able to pull 1.49 kilowatt hours out of a nominal 2.048 kilowatt hour battery. So now I'll charge up the battery, and we'll try a DC test to see if we fare better there. So the Fossibot just finished charging, so I'll now turn off power input, and I'm starting the DC discharge test again with the same electronic load set to the maximum speed possible, so 10 amps. So we'll be discharging at around 135 watts. This will probably take 10 to 12 hours, depending on how efficient the circuitry is. So see you later. So the DC discharge test just finished. we came in at a much more respectable 1572 watt hours. So the unit is more efficient on discharging on DC. The test took 11 hours and 40 minutes. And next I'm going to recharge the unit, and this time we are measuring the amount of power going into the unit so we can charge the round trip efficiency. Let me turn it on. So the battery is at 0%. Let's turn off all the outputs are already off. So now we are charging it up, and in about 2 hours we'll know how much energy the unit takes to fully charge up again. The power station just finished charging. We are back at 100%, and it took a total of 2.12 kilowatt hours. So let's quickly calculate the round trip efficiency. So in AC mode we got out a total of 1.48 kilowatt hours. Let's divide this by 2.12. So the round trip efficiency for AC charging is close to 70%, and for DC charging we got 1.58 kilowatt hours out. Again, divide by 2.12, so it's 74.5% round trip efficiency.